Welcome. Let's take a look at using the substitution technique to evaluate indefinite integrals. In this particular case, our indefinite integrals have integrands that involve trigonometric functions. So let's take a look at the integral on the left first. We have the integral of sine cubed of 3x times cosine of 3x dx. And when we're using the substitution technique, we are looking for instances of what could be interpreted as composition of functions. So one thing that I notice is that both of my trigonometric functions have an argument of 3x. So one possibility would be to let u equal 3x. Then our du would be 3 dx. Notice that there is no constant of 3 in the integral, so we would need to multiply by 3 and 1/3. So we get 1/3 sine cubed of 3x cosine of 3x times 3. So there's my 1/3 times 3, so we haven't changed the value of the integral. We've only multiplied by 1, and that 1 is cleverly disguised as 3 times 1/3, and then we'll have our differential dx. If I do this substitution then, I have 1/3, and then I'm replacing 3x with u. So 1/3 the antiderivative of sine cubed of u, cosine of u, and then my du is 3 dx. So then du. Now, let's simplify this a little bit, but I still have to deal with the fact that I have sine cubed, which maybe is more easily understood writing it that way, as sine of u cubed. So I still have another composition of functions occurring here within this cubic function. Now I could continue on. I could then say, well, I still need to do some more substituting. I could say let v equal sine of u. Then, now I've got another new variable, so my differential for v would be v prime of u du. In this case, that would be cosine of u du. And so I can see within my integral that I could replace sine of u with v. And so I would have 1/3 the antiderivative of v cubed. And then I can also see that my dv is cosine of u du, which we do have as part of our integral. So I could just call this dv. At this point, I could go ahead and integrate. I'd have 1/3 times v to the 4th over 4 plus our constant of integration. But now I would need to go and back substitute twice. So what did we say v was? We said that v, well, this will actually be 1/12 if I multiply my denominators. V, we said, was sine of u, so 1/12 sine to the 4th of u plus c. And then we'd have to substitute what u is, and that would be 1/12 sine to the 4th of 3x plus c. And that could be, or would be, our antiderivative. So using 3x would work, but is there a different choice? And the answer to that is yes, there is a different choice. So let's take a look at that. So if I, instead of choosing u for 3x, instead I thought of this integral as the antiderivative of sine of 3x cubed times cosine of 3x dx. I could think about sine of 3x as being the inside function of a cubic function. And I could think about, okay, well, what would happen if I let u equal sine of 3x? Well, then du would be u prime of x dx, which in this case is 3 times cosine of 3x dx. Now, as I look at my integral here, I can see where u would go. I would end up with a u cubed right here. And then for my differential, I can see where I have a cosine of 3x dx, which matches most of my differential du. The only thing lacking is that factor of 3. So let's go ahead and multiply this integral by both 1/3 and 3, because 1/3 times 3 is 1, and we're not really changing the integral. And I'm going to multiply by 3 here. This works because multiplication is commutative, so it really wouldn't matter where in this multiplication process I put the 1/3 or the 3. And same with the 1/3, so I'm going to write the 1/3 in front. So now I have a complete differential du. So I can rewrite this integral as 1/3 u cubed, I'm sorry, I lost my integral sign, integral u cubed du. And notice I got to this basic integral a little bit quicker than when I used u as 3x. If we anti-differentiate, we get 1/3 times u to the 4th over 4 plus c. And then 1/3 times u to the 4th, that's going to give us 1/12 u to the 4th plus c. And now I just need to substitute back in for u, and there's only one substitution I have to make rather than the 2 I did before. And we end up with 1/12 times u to the 4th, so that's sine to the 4th of 3x plus c. So there's our antiderivative. Looking at our second example, we've got the antiderivative of sine of 2x dx. So there's a couple of ways we could approach this. The first is we could simply let u equal 2x, then du would be u prime of x dx, which in this case is 2 dx. We don't have the 2. We can see that we've got this dx, but we don't have a factor of 2, so let's go ahead and multiply by 2 and by 1/2 so that we don't change the integrand. So we have 1/2 sine of u du, and then the antiderivative of sine is negative cosine of u plus constant of integration. Remember, this negative is necessary because the derivative of cosine of x is negative sine of x. And what I want is I want a positive sine of x. So I need to make my cosine negative. So I have a derivative that is positive sine. So sometimes this sign, SIGN, this negative sign, can be a little confusing when you're integrating. But nevertheless, we end up with 1/2 negative. U was equal to 2x, so cosine of 2x plus c. Now, with these trigonometric integrals, sometimes it can be confusing because there are some trigonometric identities that can come into play. So one possible derivative here integral here for sine of 2x dx is negative 1/2 cosine of 2x plus c. So let's keep track of that, and let's look at this from a different point of view. So we'll keep track of what we got before, and this time let's use the identity that sine of 2x is 2 times sine of x cosine of x dx. And then we can bring this factor of 2 in front. So 2 times sine of x cosine of x. And now as we look at this, we don't see necessarily any obvious composition of functions. But what we can notice is that one of our factors is the derivative of the other factor. So that's another way you can kind of look for applications of substitution, is that one of the factors in the integrand is a derivative of the other factor. Now, what are our possibilities? We could say let u equal sine of x dx, and therefore our du, which is u prime of x dx, would be equal to cosine of x dx. Or we could say, because sine and cosine are derivatives of each other, let u equal cosine of x, and then we would say du, which is u prime of x dx, is equal to negative sine of x dx. Now, as I look at these two options, I'm thinking this first option is easier to use than the second option, simply because in the second option we've got this negative sign that we have to deal with when we're taking the derivative of cosine. Other than that, they're about the same in level of difficulty, in complication, or so forth. So because of that little issue of this negative sign we'd have to attend to, I'm going to prefer not to use the second option. Rather, I'm going to use the first option. So we're going to let u equal sine of x, and we're going to let du equal cosine of x dx. So what we end up with here is 2 times u du. And we're ready to integrate. The antiderivative of u is u squared over 2 plus c. These 2's can divide out. And we said u was equal to sine of x, so this is sine squared of x plus c. So at this point, you might be thinking, wait a minute, we didn't get the same antiderivative using both strategies. Well, the reality is there are some trigonometric identities that can help us connect the two. So let's just take a quick moment and take a look at that. So at the moment, it appears we have two different antiderivatives. But let's go ahead and explore what our negative 1/2 cosine of 2x plus c solution would look like if we applied some trigonometric identities. The first identity that we might want to consider is that cosine of 2x is equal to 1 minus 2 sine squared of x. And right away, we might be starting to see a connection between our solution on the right and our solution on the left. So we would have negative 1/2 times 1 minus 2 sine squared of x plus c. We can distribute our negative 1/2. And negative 1/2 times 1 is negative 1/2. Negative 1/2 times 2 is 1. So we would have 1 times sine squared of x plus c. Let's go ahead and think about using the commutative property of addition. So sine squared of x minus 1/2. I actually want to write this as plus negative 1/2 plus c. So I've got sine squared of x plus negative 1/2 plus c. Now remember, c is just an arbitrary constant. So what happens when I take any constant and I add negative 1/2? Well, if I take any constant and add negative 1/2, I just really get a new constant. So regardless, this is simply just another constant. So my antiderivative is simply sine squared of x plus some constant. And so you see the two solutions are really the same, even though they appear different. I hope you find this helpful.